to discuss the parabolic and hypoelliptic case. So actually, I don't have time to do this one because there would be a lot of repetition, so I'll focus directly on that. Just a comment so that you see the steps. So let's say an introduction, a transition from ellipticity to elliptic case to these cases. So the elliptic setting that we have been looking at was this. A matrix depending on x, grad f equals 0. At various steps of the proof, we consider sub-solution, super-solution, but that's the main equation. And we derived, conclusion was we derived the local Hölder regularity. That's the main conclusion. I also told you, I won't have time really to cover that, but we also obtained it in hypoelliptic case. I also told you how Moser was the first to obtain something even stronger than Hölder, which is the Harnack inequality. The parabolic case was the case naturally considered by Nash, 58, and the Giorgi, 57. And the parabolic case is exactly what you would think it should be. It is just this. Now your matrix depends on t and x, and it's like that. Okay, so just to acclimatize yourself to this new setting step by step. So here, a sub-solution would mean dtf less than that. Right, just like before, sub-solution was greater than 0. And super-solution is less than. And everything is consistent. You make the same assumptions on your matrix. Okay? And you assume that it's a symmetric, measurable, matrix-valued function. Same thing. Okay? And the conclusion, first obtained by Nash, but later on the De Giorgi approach was extended to this. I'll say a few words because I'll reuse it in the hypoelliptic case, which includes that as a subcase. The main result, again, is the Hölder regularity. And again, the Moser, 3 years later after the paper I presented in the last lecture, Moser also extended the Harnack inequality to parabolic equations with rough coefficients. Just observe also that this is a good intermediate step because we have a first-order vector field on top of the second-order operator. So the scaling is modified. That's what I'm going to give you. And I will skip the rest of the proofs. But it's not interesting from the viewpoint of Hörmander hypoellipticity. Right? You don't need to commute anything. You have all the diffusions in the direction dx, and then by difference you control dt and you're done. It's not an hypoelliptic operator. It's what we call a parabolic equation. So before we go to the hypoelliptic setting, so again the main result is Nash 58. Harnack, this is Moser 53, but there was a small gap in the first proof published, which he corrected in 64. The Moser approach is significantly less friendly in the parabolic case, surprisingly. Okay, so let me keep things here. The scaling in the parabolic case is this. Tx gives r squared t rx. You just have to respect the balance of the differential operators in your equation. That's for the scaling. For the invariances by translation, it's again translation invariant in both variables t and x. The elliptic problem was translation invariant in x, now it's translation invariant in t and x. the cube, the ball have to be replaced by cylinders. We don't really want to call them balls anymore. That would be inaccurate. And the cylinders now are usually denoted like by Q. So the base cylinder, just like the base ball, without pun, is conventionally in this field is not centered around 0 in time. It's finishing at time 0. It's a cultural thing. I mean, you could change it if you want, but since like hundreds of papers are written like that, let's adopt it. So the base cylinder will look like that. This is the usual way to represent it. Time flows upward, and this represents my variable x, not necessarily 1D, but it's schematized like that. And this would be QR. So QR would be in time minus r square 0 included times the ball in x of size r. Okay, so that's the usual ball in Rn. You can see that the cylinder respects the scaling. So it's like a baby step towards the hypoelliptic scaling. In general, obviously, for a general differential operator, you'd have a Lie group, but we don't need some sort of pretentious structure like that. It's very simple in our case. And so the time 0 is here. This is time 0, and this is time minus r squared. We're never solving parabolic equation backward. I'm sorry, I had that question sometimes in talks. It gives this impression, but we don't do this. It's just a way to represent. Okay, so that's the scaling and the translation. For the rest, something important is that as compared to the elliptic case, we observe my endpoint in time doesn't change with the scaling. And it's exactly what we intend. If I'm writing Q1, time will start at -1, and Q1 half. Of course, my drawing is not really at the scale, but will end up at time -1/4, right? But the two cylinders touch each other at the final time. Okay, so that's the way. And now, if you replace B1 half, B2 by Q2, Q1, Q1 half, all the statements literally I gave you in the elliptic case carry on to the parabolic case. The fact that I pushed the initial time when I reduce the cylinder is what makes sure that in the parabolic case I leave a time gap, I leave a little bit of time before any regularization property happens. Okay, so there's no contradiction. Now, let's go to the hypoelliptic setting. Which was the main goal of these lectures. So now I'll make one connection with the motivation and we'll study a model case. So we are going to study something that has many names, sometimes called the Kolmogorov equation because of the article of Kolmogorov of 1934, the short note actually. I mean, he really never gave a name to it. You know this equation for the time-integrated Brownian motion, the law of it. And sometimes it's called kinetic Fokker-Planck. It's also sometimes called the Langevin equation with inertia. I mean, I'm not sure about the names in probability, but it has many names. So kinetic Fokker-Planck and so on. Now, for the motivation, let's make sure we make a connection with my first lecture. I remind you that the lambda equation, which is the fundamental equation for collisions in plasmas, writes like So I don't want to rewrite the complicated collision operator. I just want to remind you that it writes like that. So now my unknown f is a function of time, x and another variable v. Okay, time, of course, is real. X and v both live in Rd. Okay, and that will be equal to divergence in v times a certain A matrix that depends on f plus B that depends on f, a vector. So this one is a vector dot grad v of f plus C that depends on f, f. Of course, the C is just the divergence of B. And for those of you who are familiar with the Landau equation, C is actually a constant times f. Okay, C is the convolution of f with a Dirac, in fact. It's the most singular part. So the main result is the following. So what we do is we imitate the Giorgi and Nash, because we don't know how to solve in general the Cauchy problem for that equation. We'll assume that these coefficients are given, even though they are nonlinear, with low regularity, and try to see what we can obtain on this equation. Okay, so we trade a nonlinearity for linearity with low regularity coefficients. And the main result is as follows. We'll only do a subset of this where I will drop the lower order term to make life simpler in these 2 hours. But the main result, which is proved in the paper with François, Cyril, and Alexis, 17, I think, we prove that solutions to this, so it looks like I'm rewriting the same equation, but not quite, because now the coefficients are given. Now that this is a linear equation, so this linear equation with A, B, S measurable, and all the other assumptions you would expect from what I've said before. A is a symmetric matrix-valued function. And I also want to assume that A has a bound above and below for some lambda strict positive. I want B to be bounded, so B is a vector. So B is everywhere bounded, and S is everywhere bounded. So these are L infinity bounds from above on the coefficients of the lower order terms. Okay, so if we assume all that, let me stay here at the level of the linear equation and tell you what we obtain here at the level of the nonlinear equation. Then we establish that if f is a weak solution in, so I'll have to tell you what it lives in, L2 of an open set. In fact, it will have to be L2 L2tx h1v of the open set inter L infinity in time L2 in xv of the open set. I mean, you can check it later if you want. That's very similar to what you do for Navier-Stokes. It's just the space associated with the energy estimates. Then f is locally Hölder continuous. I'm not being very precise, but you can make the bound, now you can make them quantitative. In the first paper, we had a contradiction argument for the key part, but we removed it afterwards. And as a corollary, which is detailed in the same paper, we obtain that if F is a solution, of course it's always weak solution I'm talking about, weak solution to the lambda equation in so I want F to be L1 in Tx, L infinity, what will I put? L infinity in T, L1 in xv with weight 1 plus v squared. This is the mass and the energy. And I'm going to put something very strong, L infinity in Tx and v. I'll explain in a second why I'm using that. And a priori bounds on the a priori bounds on all the hydro fields. You remember the averages in velocity. Then F is Hölder continuous. Again, I'm not being too precise here, but so this was a step.
Just to make sure. So before the U was for the position, so now U is the domain for the position, but the velocity is unbounded.
Absolutely. Where now U is an open in R for time, cross RD for X, cross RD for V. But I mean, this is the only time in this statement I will take a general open. After, in a second, I will stick to cylinders. Because you want to prove local regularity, so in the end, you only have to work in a cylinder. So this statement is one of the steps in the conditional regularity program on the lambda equation, but there's one thing in it that is very unsatisfying, which is this. The a priori bounds on the hydrodynamical fields, we know we expect them to be true because so far no one has any idea for solving the general Cauchy problem for inhomogeneous kinetic equations. But that is annoying. We would have loved to just stick to uniform bounds on the velocity averages. We need that bound because, so I'm not saying infinite is the optimal exponent, but we need a high exponent that we don't know how to prove anyway. And it's connected to the bound we use on the source term. Again, that is not optimal. We could have a Lebesgue, a certain Lebesgue, but I don't want to make the statements too technical, because S is directly related to this term. Okay, and to control the source term, we need some sort of high integrability on the solution itself. So although it solves one of the steps of the regularity program, it assumes something that it explains the gap in the conjecture presented, the problem number 2. And that the bound missing, as compared to what we want to assume, was obtained by Silvestre 2016, I think, only for slightly less singular, a sort of modified version of the lambda equation, the one that is the moderately soft potential one. You remember when I gave you this gamma? For slightly less singular non-physical equations, this gamma greater than -2. So that is the exact reason for the gap at the moment. There's something we are missing here about the L infinity bound. Okay, so that's the...
To understand, so, but
yeah,
because this L infinity bound is more related to dispersion to avoid that the F square goes too big compared with...
F square goes to...
big Fx square compared with regularity, which is much more local, or...
No, well, no. I mean, if you want to identify what it is a sort of gain of integrability in space. You know, the hydrodynamical field. Let me write it with another color. What sort of bounds they are? schematically, I'll continue with my schematic Lebesgue spaces in different variables. You assume stuff that are of type, L infinity in Tx, L1 in V, possibly with weights. So that is what you assume. And you ask whether from that you could go to this. It's a gain of integrability in the last kinetic variable. What is very frustrating is that it looks like, that's what I sort of speculated in the first lecture, it looks like the recent progresses on the spatially homogeneous problem could help us. This is really a problem of understanding a gain of integrability on the last kinetic variable. But of course, everything is mixed in the variable during the evolution. So that's what is missing. And what I'm going to do in order to have a chance to present some non-zero amount of the proof, I'm going to drop the two lower order terms. I know there is a subtlety with the source term, but in some sense, in the proof, obtaining the exact Lebesgue exponent the best you can from the method on S is really technical. There's no conceptual idea associated with how you deal with the lower order terms in themselves. So I will drop this. And this is my model equation for these 2 hours. OK, so now we finally arrive at a clean, I can make a clean statement. Yes, so the model problem is the following. I'll just study dtf plus v grad xf equal divergence A. So don't forget my A potentially depends on all variable, grad vf. That's my model problem. I will look at it so for one last time, I write time starting at 0, but I'll adopt the notation of the parabolic community in a second. So I'll end my times at 0. And here we have an omega open in x and v. rdx, rdv. And in fact, the model case I will look at will look at something like a cylinder. So I have to discuss now the scalings. I will look at a cylinder within this open set. OK? So, and the assumptions on A, I'll write down the cylinder and the scaling in a second. I don't have lower order terms anymore. A is, as always, symmetric, measurable, and satisfies A squeezed between my two bounds. This is always the same key assumption.
Yeah. In the real normal equation, we have the non-degeneracy of AF, because in that case we will have collisions only on the orthogonal directions, and this is not degenerate. This is not.
Very, very good point. So I skipped completely that. Yeah, for the true lambda equation, you need to use the bound on the hydrodynamic fields in order to bound the ellipticity matrix. It is true that these are bounds with weights, and the weights are different in different directions. And A itself is an integral on F, and you need to prove it's quite technical, but it works. You need to prove that with enough a priori bounds, you find enough mass in this convolution in order to bound your matrix as you want. But I think part of your question is where are the weights in different directions? You do not see them because I'm only discussing the local regularity. But it's an important problem. In some papers, you try to quantify how the regularity bounds depend on the velocity for large velocities, and then you have to exactly look at these weights and everything. OK, so let's go to, I'll give one theorem, and then let's start the scaling and the proof. Where is the... So main statement, that's the main problem, and the main statement now is it is first proved by Wang and Zhang in 2009 and 10 by a modification of the Moser-Kruskov argument, let's say. And we proved it again together with the Harnack inequality in this paper with François, Cyril, and Alexis. So the main statement is, you can wonder why we reproved it. That paper, it turns out to be correct, but it's one of the most badly written paper I've ever read. But I mean, still, the idea is interesting in the paper. It's it goes back to the discussion of the importance to write papers well. Otherwise, someone will try to reprove differently what you've done. So, given f, a weak solution, weak solution to my model problem. In what is the setting I'm taking? I'll take this setting. I'm absolutely not trying to put the minimal functional setting. I just want to put a functional setting reasonable for all the manipulation I'm going to do. Don't forget that in practice, it's rarely the problem, the tiny optimization of the space you're looking at here. What did I call it? Omega. And then I have this, and with notation I hope will be clear, like that. Okay? So that's exactly what you obtain from the energy estimate. In fact, you could assume less and recover it from doing the energy estimate manipulation. And A satisfying this hypothesis, let's call it 2 star. Then the conclusion is exactly the same as in the elliptic and parabolic case. There exists an alpha so that f is local Hölder in where the domain you're looking at, but in fact you have a slightly more precise estimate, exactly as in the elliptic case. You take something compactly embedded in omega, and then you take a T0 strict positive in order to maintain a gap away from the initial time. And then you have that your local Hölder regularity in T0 T time omega tilde is less than F L2 everywhere. Okay, L2 on your whole stuff. And of course, your constant depends on the distance between your compact subset, as always, and T0, and the dimension, and lambda. The dependency is exactly as similar to conceptually to what we've done before. Okay, so that's what we want to prove. And there was also Harnack first obtained here, and but I probably won't have time to do Harnack. So now, let's do the scaling. It will be one more step as compared to the parabolic scaling. So, modification. Every section now in the rest of the 2 hours will be a modification of a previous step. So the goal, don't forget what we've done before, it was supposed to help what I'm doing now. So modification of scaling, invariances, and cylinders. As always, you remember, by invariance, I mean the class of equation is invariant. Star and 2 star together. So the right scaling now is txv gives r squared t v. Let's start by that, or rv, sorry. So that is no surprise, because if you would forget x, you have exactly a parabolic structure between t and v. And then the x variable, because of the grad x and the v, has to have this form r3x. So that is the hypoelliptic scaling. So if you scale the variables like that, you will maintain the same equation with a rescaled matrix A. Okay, and then for the invariances, well, you have, in terms of translation, you can still translate in t and in x. I mean, that becomes familiar, because with the 3 variables, we are now in the classical mechanics. You know the laws of time translation invariant and position translation invariant. But in velocity, it's not exactly a translation. You have an invariance when you account for the inertia principle. So this results in the Galilean transformations. So Galilean translations, which is, yeah. If you start from point tx naught v naught, you will obtain t naught plus t, x naught plus x plus tv, v naught plus v. And the additional term here is the inertia principle, right? Because if you change the velocity, you of course have to time integrate what the impact it has on the position. So once we have covered these 2 invariances, we modify the base cylinders appropriately. So remember, the cylinders play the role of the balls in all the elliptic theory I've covered before. So now the base hypoelliptic, I could call them kinetic if you want, but I mean in principle hypoelliptic would be more general, because kinetic is a particular type of hypoelliptic PDEs. So the base kinetic cylinder would be QR, which could be written as RQ1, where the left multiplication just account for my scaling law. You know, it means you multiply first variable time by r squared, second by r cubed, third by r. And my base cylinder is exactly what you would expect. So QR times is vertical. Now the horizontal line is x and v. And QR is just minus r squared 0 times a ball of radius r cubed in x times a ball of radius r in v. That just follows the scaling. Now you could translate, I mean, I'm mentioning it, meaning all the statements I give are invariant by this and the translation. But of course, I won't rewrite them ever again, because I don't want to make the statement too complicated. But you have the translated kinetic cylinders. Let me write it once, that respect the Galilean invariance, which writes like that. Q scaled by R translated by Z naught is equal to a non-commutative law. Let's write it like that. Z naught circle QR, the base 1, sorry. So I'm applying the law which corresponds to my formula here. That's all. And that means the following. So these are the times satisfying this, and the position x satisfying this, and the velocities satisfying this. Okay, so the only thing to be careful about, that's pretty, you get familiarized with that pretty quickly. You just have to be slightly careful because this is a non-commutative law. So left and right have different outcome in your calculation. Okay, so now that we have the scaling, I'm going to follow exactly the structure that I exposed before. Still the one that goes back to the Giorgi. I'm going to tell you how to extend the first lemma and then the second lemma. So, modification of the first de Giorgi lemma. So the main difficulty, just as a guide, the difficulty is the lack of ellipticity in X. I'll discuss. You might say, well, what do you do with T? But like I said, T, the vector field dt is not a vector field you have to recover by a commutator. I'll explain that to you with the energy estimate. I didn't do the energy estimate in the parabolic case, but the one I'm going to do now is more general. If you do the energy estimate carefully, you can recover immediately again L infinity of integrability in time. So that's not the problem. The problem is X. And I will give two arguments. One that is less sharp and maybe slightly, maybe less slightly direct if you want, but I think more robust for some application. One is based on averaging lemma. So I have to be careful with the statements I give because I have the father of averaging lemma in the room. And the second one is based on reducing to the fundamental solution of the Kolmogorov equation. And by that I mean, by the Kolmogorov equation, I mean when A is identity. So I just mean you reduce to studying the fundamental solution of that. So you can see why this method will lead to sharp results, but it's cheating a little bit. It's just because you know them explicitly. Yeah.
Are there also options with brackets or these commutative methods? Or?
Yes, sorry. Yeah, you're thinking, for instance, to do calculations of Bouchu of some years ago. Yeah, sorry. I was. For me, all of that was part of this type of proofs. The way you recover the transfer of regularity doesn't matter in some sense for me. I will tell you how to do it with one statement of averaging lemma, but you could replace it by any statement of transfer of regularity. So yes, but I was just calling all that averaging lemma in some sense. The second method is, in some sense, it's great when you have access to an explicit fundamental solution. But in many situations, you could imagine, maybe one day this approach will be applied to equations in tricky geometric setting where you don't have access to the explicit solution, the fundamental solution. And then it could be useful to have a less sharp but more robust approach. So this approach came later, even if I presented earlier because I was involved in that one. This one was first proposed by Pascucci in a very nice paper, Pascucci and Polidoro in 2004. Actually, this paper also contains a way to reprove averaging lemma that I think is not the right way to do it, but it's very sharp. You'll see that in a second. Okay, so let me give you a statement, and then, yeah. Just to prepare yourself, I won't do the whole thing because part of the proof are exactly similar to elliptic case. The part of the proof I will redo is the localized energy estimate and how to obtain the gain of integrability a little bit above 2. And then you can run the Giorgi Moser iteration exactly similarly. And that I will skip because I don't have that much time, okay? So let me give a statement. Lemma. So hypoelliptic, sorry, I said hypoelliptic. Let's just say kinetic first, the Giorgi lemma. And it was first proved in the paper that I mentioned of Pascucci and Polidoro. So you consider this equation. Very often, just to make the calculation slightly more compact on the blackboard, I will write the transport operator calligraphic t. Okay, matcal t will be always dt plus v grad x equal to this. So I consider this equation, and I consider f a subsolution. Okay, f subsolution and a weak subsolution. And the functional setting, so there's a small subtlety, which is if you want to be able to justify all the manipulations on subsolution, you have to be slightly more careful. So I'll put slightly more assumptions on the weak subsolution. So it will be L infinity in time, L2 in xv, inter L2 in time, L... which one do I need? No, maybe, yes, this one, L2 in time and X, H1 in V, sorry. So that will be my framework for F, but I also add that the transport operator of F is, for instance, L2 in time and X, H minus 1 of V. Okay, so maybe I have to say a word on that. I certainly, I'm not giving you the most general statement, but it's not something I find extremely interesting to fight about the spaces. Think about a subsolution means, in fact, an equality with a defect measure. The defect measure can be less regular than H minus 1. If you know that F is H1 in V, that object will be H minus 1 in V. So that is certainly not the larger space you expect a subsolution to live in. And indeed, this assumption can be relaxed, okay? But assuming that helps to justify a lot of manipulations later, okay? So we want a notion of subsolutions on which we can do a priori estimates. That's the moral of that, and I won't repeat it each time. A satisfies the 2-star assumption as before. Then, so let me formulate it like the Giorgi as a tribute, let's say. There is delta strict positive, so that the positive part of F, L2 in Q1 less than delta, implies L infinity of F plus in Q1 half less than 1 half. And if I still have my cylinders somewhere, yes. Yeah, okay, maybe I should do a drawing instead of redrawing. So as compared to the elliptic case, you see you have a time arrow on the variable, on the time variable, it's irreversible, so you have a time direction. So the picture looks like that. This is Q1. You assume here that you have not much L2 norm, and then on Q1 half, which actually is smaller than that, in fact, like that. On Q1 half, you deduce that F is less than 1/2. So here you have F, it's F plus, but that means the whole F, and here you assume the positive part as small L2 norm. Okay, so that's a picture that is quite similar to the elliptic setting. The key thing now for the proof, for the two proofs, is that the De Giorgi-Moser iteration has the same, exactly the same structure. And you can adopt the viewpoint of De Giorgi with energy level, or the viewpoint of Moser with increasing the Lebesgue integrability. They both work. So I won't repeat it. The two steps that are modified, that I will do now, are the energy estimate, the localized energy estimate. It's not very hard, but it's worth doing it once. And the gain of integrability, LP in all variable for some p greater than 2. You remember, and in De Giorgi, then he iterates on the energy level, and in Moser, he iterates, he gains then p, then a bit more than p, reapplies and reapplies. So first approach. Oh, and sorry, and the localized energy estimate is common to both approaches. So that I can do now, and of course I won't repeat it. The proof by averaging lemma and the proof of Pascucci-Polidoro, they both rely on the localized energy estimate. So let me do that now. Localized energy estimate. So as always, in your, maybe I should write it once, in your iteration you do something like that. Let's call it Q tilde. So that will be Q1/2 plus 1/2 Q2K. I hope I write it correctly, I think so. So you see that the first one is Q1. You start here. And the infinite one is Q1/2. That's exactly the equivalent of my sequence of balls in the De Giorgi initial paper. Okay, so you have a sequence of cylinders that get closer and closer to the final one. And here you take a localization function, smooth, that is 1 on the Q tilde K plus 1 cylinder, and whose support doesn't get away from the Q tilde K1. Now you check how much space it leaves between the Q cylinders. You have a negative power of 2. You remember the scaling in the variables. You check that. So I'm going to skip the very boring calculation. And you obtain that the gradient of T xv of phi is bounded by a power of 2 of that style. 3 times dimension times k. I've not tried to be optimal here, because it's the worst variable. The gradient in x is the worst one, and you pay a cube. I mean, anyway, the only thing that matters is you get a geometric power in k. So you have a localization now, and then you integrate. So in order to be as close to the energy estimate I really did in full details 2 lectures ago, I will really adopt the same setting. You integrate your base equation against F minus a potential energy level So that would give you the energy estimate perfectly ready for applying the De Giorgi iteration. Positive part, and then the square of the localization function. That's exactly what we were doing in the elliptic case. Okay? So let us do that. So that's here that the compact notation for the transport operator will prove useful. I will a lot of time I will drop the domain because the domain is imposed by phi, the localization function. Everything, you can see that the support of the localization function is always included in the larger cube in which I have defined my weak solution. So I never have any problem. So transport operator applied to transport operator applied to f against f minus e plus phi square is less than, I work on sub-solutions, you remember, divergence A gradient phi and then f minus e plus phi square. So to do it rather quickly, we'll do exactly the same as in the elliptic theory. We note that because it's a gradient, you can replace, that restricts this whole integral to where this is non-zero. So you can replace that under the gradient by this. You can also replace that under the derivatives here by this. Okay, and you do one integration by part here. So here you also remember that t is dt plus v grad x. So you do an integration by part on that term as well. And you do an integration by part on that term. Okay, so for that one, in x, there's no boundary. Because I know it's not super apparent on my drawing, but x variable lives on this horizontal line and you have a compact support here. So there's no boundary term. So the integration by part gives you only when t goes on that. And because in fact, okay, sorry, let me write it instead of talking. You can say, because it's a first order operator, you can rewrite it like that. First step. Then by doing your integration by part, you just observe that this part has no boundary term. So I write first the two volume term, which is this. And then I have one boundary term, which is in time. But don't forget, in time, we do integrate from minus 1 to 0. And phi has compact support before that. So there's only the final time that shows up, which is great because it has a positive sign. And you have the integral in xv of f minus e plus over 2 phi square, all of that taken at t equals 0. That will be treated as an error term. That is positive. We want to keep it. On the right-hand side, the integration by part has no boundary term because we are in V and we have cut off V is also part of this horizontal representation where there's compact support. And we get minus A grad V F minus E plus dot grad V F minus E plus. So I have this term first, phi square plus, or minus, sorry. And then there is the case when the gradient hits phi, and I get twice A grad V F minus plus dot grad V phi F minus E plus. Okay, so you can see that what will happen here is exactly similar to the elliptic theory, but we have this term on top of it. So let's collect everything. I'm collecting everything, and I will use the bounds on the matrix A. Collecting plus using, as always, the bounds on A. You get 1/2 of the integral in x and v of this at time 0 plus I collect the first term that has a sign. The first term comes with the 1 over lambda square of gradient f minus plus squared p square. So I collected the first term, and now on the right hand side I have two terms. I have 1/2 of f minus e plus squared t phi squared, and the other term is plus 2 lambda, I bound the matrix A, gradient of f minus e plus gradient of phi in V times phi times f minus e plus. And now this is the same trick as always. On the last term, you're going to do Cauchy-Schwarz and kill the grad v of f by this one. This is always the reason in all these estimates where I told you there is the Hilbertian square on the localization function. It's because of that. You square that part, you kill it by this term, as always, and you end up with the kinetic Cassiopeoli estimate, let's call it like that, to sound a bit Italian. Kinetic, okay, Cassiopeoli, there's 2c for sure, then 1p, I guess, and 2l, right? 2p as well, and 2l? 1l. Ah! Okay, so 2p and 1l. Kinetic Cassiopeoli inequality, which is the following. So you have to collect, you have to look in the eyes, my last display there, and you collect everything, and you get 1/2 integral in xv of f minus e plus squared phi squared at time 0 plus integral gradient of f minus e plus squared, it's a gradient in v phi squared. This is integrated in all variables, less than. So you'll have to do it carefully to see why I put these exact powers in lambda, but it's what it is. So you have various n infinity bounds on the gradients and the transport operator on your localization function times, and you will recognize the last term as a form that is reminiscent of the Cassiopeoli estimate in the elliptic theory. Here is it. Okay, so that's the core localization estimate. It's very similar. So we have one good news compared with the elliptic theory. The additional t variable is dealt with by this term. Why? Because ending up at time 0 was arbitrary. I could have redone the same estimates for all the intermediate final times. And by doing that, I would have controlled point-wise all these L2 time slices. Okay, so that's why this term gives you actually an estimate, L infinity in time, L2 in xv. It's the sum of two positive terms, so I can focus on the first one if I want. The second term gives you a nice bound on L2 tx h1 in v. Obviously, what is missing here is the the regularity in X. So that's what is where the two approaches I mentioned diverge. I'll do that and then we can do the small break. So first approach. Approach 1, based on averaging lemma. So averaging lemmas are, oh, there's one thing more, sorry, there's one, yeah, okay. Maybe I'll put that on this blackboard. Something I don't want to spend too much more time on is that if you would take phi as, like I said, on between my two balls, my two cylinders, q tilde plus 1 and characteristic function q tilde k. You have bounds on the gradient, so you have a power of 2 here, and it looks exactly like the localized energy estimate we had before, except that the left-hand side doesn't control an LP greater than 2 in all variables. That's the only difference. Okay, so if I tell you, if I patch that by giving you an argument for improving what you know on the left-hand side to an LP greater than 2, the rest of the proof works exactly the same. So I'll just do that. Approach 1, well, it is based on averaging lemma. So let me give you an example of, there are many possible statements, but one statement would go like that. If you consider f in L2 of all the variables, and you can consider my second condition also as a sort of function space, so that the transport of f is in, for instance, LTX h-1 v. I'm not choosing that at random because h-1 is what you expect my right-hand side to be in. Then, for phi var phi, let's say, as a function of v, smooth compact supported in RD, then integral of f var phi dv, which now is a function of t and x only, is in some hs of R1 plus d for some s strict positive. Actually, I think the optimal one you would get is 1/3, to be checked. Forgot to put that in my note. Maybe François remembers. I think it's 1/3 in this case. But anyway, it's strict positive. Okay, you lose a little bit compared with the standard averaging lemma just because I put some negative regularity on the right-hand side. But it doesn't really matter for us. Now, there's one problem, which is that a sub-solution transport of f less than grad v a grad v f is not there in general. Okay? That does not imply transport of f L2tx h-1 in v. Is that clear? Because the defect measure could be less regular than that. But it looks like an annoying problem, but in fact, because we ultimately are just trying to establish a gain of integrability, in the end of the day, we go through energy estimate and Sobolev spaces, but we forget about them once we have obtained the integrability we want. So a Sobolev estimate doesn't survive comparison, but a Lebesgue space does. So it is enough to work on to work on f, let's say f bar, a true solution, a weak solution, so that, so our solution is non-negative anyway, 0 less than f bar. Then f bar is a true solution where f bar satisfies the energy estimate. So how do you do this? You make sure f and f bar coincide at some initial time, and then you derive the same estimate on f bar. On f bar, you can apply the averaging lemma. F bar satisfies the previous lemma. Let's call it lemma AL. So it's a positive, non-negative function. So you deduce that f bar, it's not so hard to prove that you need a little bit of moment, but all of that works. Everything is localized, don't forget in the end. Your f bar will actually be will actually be hs in tx. So some small x time L1 in V, all of that is local. Why do I claim that? Because if I can control some average here and f is non-negative locally, it's an L1 norm, right? I'm just giving you the argument schematically. You need to localize everything to make that fully rigorous, but you'll gain some small Sobolev on L1 in V, and you combine that with the information from the energy estimate, L infinity in time, L2 in xv, and L2 in tx, h1 in v. Now if you shake all of that and you interpolate, you get that f bar belongs to some LP in all variables. Let's call it LP star to really mimic the notation in the elliptic case for some P star strict positive. And all of that is local. Okay? And once you have obtained it on f bar, this implies f bar in LP star lock implies f in LP lock. LP star lock. Just because the two functions are compared. So the second method, maybe I should do a little break now. Okay, maybe I'll explain the Pascucci-Polidoro argument after the break. Let's do a 2 minutes break, yeah. 5 minutes because I have to. I will just explain the second approach, but maybe without doing all the technical. I'll give you one statement that is correct if you want to recheck it, but maybe not all the full details. So the other approach by Pascucci, maybe I won't write the Italian names anymore, just the initials. Pascucci and Polidoro. Their idea, I suspect at the time they wrote the paper, they didn't know about averaging lemma. They had not met François yet. So what they did, they look at a problem like that, sub-solution of solution, and what they said is let's add artificially the missing part to recreate the Kolmogorov equation. So here it would just correspond to removing identity in the matrix. And let's call that K of F, this all operator, K for Kolmogorov. They have K of F is equal to a second order operator like that. Sorry, I forgot one parenthesis. And the next step is to say that that Kolmogorov operator, because we know the fundamental solution, we know very precisely the regularity of a solution in terms of the right-hand side. So they will write down F as a sort of convolution. That's where maybe, because I would like to discuss the second lemma of the Giorgi, so that's maybe where I will skip some detail. The convolution is slightly modified because it's a convolution taking into account the Galilean translation. So it's a convolution for a slightly modified non-commutative law, but okay, it's a convolution morally with the right-hand side. And now their idea is that we integrate by part 1 grade V onto the fundamental solution kernel. And you see what happens. And you see that you're still able to control some Lebesgue space in the end. You perform careful Young inequalities and it still works. I'm going to give you a statement that justifies all that. But that is the moral. The moral is that they really treat that as an error term. They look at how it goes through the fundamental solution. They integrate by part 1 grad V. And of course, on what remains here, they use the energy estimate to say that this whole thing is L2. Right? The energy estimate controls grad VF in L2. And this A minus I is bounded L infinity. So, for those of you who know already well averaging lemma, you can see that this is a way to reprove averaging lemma when you're, for very simple equations which you can reduce to the constant coefficient. The moral of Pascucci-Polidoro argument is to say that grad V of the fundamental solution of the constant coefficient is mapping convoluted with L2 gives you more than L2. That's the moral. You could say, well, can you get some HS from that? In fact, you can as well. I'm going to give you that now. So, of course, when you can do that, it's very quick. It's very nice. It hides a little bit. In some sense, it's not a very good approach for more complicated equations. It's not very robust. You don't really see the geometric aspect of the averaging lemma when you do this. So, for instance, one statement. So this is a correct statement. If you have F non-negative at least L1 lock solution to or you can put it better or whatever, L2, it doesn't really matter. You just need to be able to perform the estimates. K of F is equal to divergence V capital F1 plus capital F2 minus M. So, okay, what do I mean by that? Capital F1 is meant to be what's inside the parenthesis. So I want capital F1 to be L2, capital F2 to be L2. So this one, you could forget it now because it was for dealing with lower order term. But anyway, you can put it. It really costs nothing in this lemma. And M is your defect measure. And M, you will want to bound it in a total variation norm on measure, which I call M1. The main statement is that you can bound F LP like, so you have a coefficient, well, let me give it to you for once, plus 1 over D minus P F1 plus F12 plus F22. So no surprise here, when you just try to compute an LP norm, the defect measure doesn't appear. Okay, so think about the first approach. I made it very clear in the first approach that if you're only interested with an LP norm, you can drop M and work on an F bar above F so that there's no defect measure. So that's not surprising that that first estimate is not depending on the defect measure. And the P here is something between 2 and 2 plus 1 over D, which is the critical exponent. So you gain something here. And in fact, if you're willing to pay a price in the total variation of the defect measure, you have, for instance, a regularization like that. So a weaker form of that was recovered by averaging lemma in the paper with François. But you can really, when you have access to the fundamental solution, you can really discuss the maximal regularity. So this one is, for instance, I wrote it, for instance, in L1. And here it's M1. So this second statement tells you that if you're willing to estimate all these terms with an L1 norm, actually you can even access some amount of X regularity. And here sigma is between 0 and 1/3, which is the critical regularity exponent. Okay, so how do you prove this?
This is regularity in V or in X?
Sorry, what did I wrote? In X. Sorry. Thanks. Yes, so in X. So the way to prove that, the only thing to be really checked is that my exponents are correct, but it's kind of believable that you would get something like that. I certainly won't do the whole calculation. I will just drop the formula for the fundamental solutions of Kolmogorov that I already mentioned. You just need to you use that f in fact is integral of g t minus t prime x minus x prime minus t prime v prime v minus v prime, and then the right hand side. Like I said, it's a convolution modified by the inertia principle, and then g txv is just 1 over 4 pi square t 4 d over 2 exponential minus 3 x minus t over 2 v squared over t squared minus v squared over 4t. And then what you need to prove is that the grad v of g, and you also need to estimate that, because when you differentiate in v, you pay a price because of that dependency. So you need to estimate both these things, and you can check that they are bounded by, I mean, that calculation is extremely simple. It's just, you just do differentiation of that, and you have the same argument in the exponential. And now you just observe what is the integrability of that. That's all. So that's how you prove the LP. For that one, you need to work a little bit more, but okay. Since I won't be using it, to prove the LP, you just check the integrability of that. And then you localize the estimates. Okay, that's another step I'm gonna skip. So I make it look longer than the first approach, but I mean it's still quite short, in fact. Okay, one last remark that I might skip, otherwise I won't be able to deal with the second lemma. I wanted to show you the argument for which in the first lemma, yes, you can even start with a lower integrability. I won't have time, but I promised you that last time, but you can, by a small additional iteration, You could even start with anything like L1 if you want. Okay, so let's, in the remaining time, let me deal with the second lemma. And again, because of lack of time, I won't be able to do the two approaches. We first proved it by a contradiction argument, but I will directly jump to the quantitative method. So let's give a setting and a proper statement first. So modification of the second de Giorgi lemma. So the second de Giorgi lemma as such is not proved in Wang-Zhang. They don't really follow this route. The first time it was proved in the kinetic setting is in the paper with François, Alexis, and Cyril. And really, here we used a contradiction argument with a little bit of something reminiscent of homogenization that François came up with at the last minute to save the proof. So there is a contradiction argument here. And later, with Jessica Guerand in 22, we gave another proof based on Poincaré inequality plus trajectory, which really is what I prepared you for with all my three arguments, which I spent a lot of time on in the elliptic case. And at the same time, Jessica and Cyril, 22, I think, same time, they combine Poincaré, a sort of modified Poincaré, Poincaré modified plus Kruskov. And after this paper, we vastly improved the method with Anceschi, Jessica, Amélie, and in another paper, Lucas Niebel and Zacher and Helge Dieter. I mean, we wrote two papers here. And there's another paper we took a lot of inspiration from by Lucas Niebel and Zacher. So there are 4 papers involved in total. And I will try to give you the simplest ID from all these papers in order to not... Because of course the first one was making things a little bit more dirty than they need to be. We had more error terms than needed. So in some sense we follow very much the ideas of Nash, Moser, and Kruskov. And in the paper we are writing right now with Lucas, Rico, and Helge, we really also show that you can follow the original Moser approach, which is what we wanted to do a long time ago with Cyril, but didn't manage to. So, theorem. Well, no. So my theorem, yeah. Sorry, I realized I didn't put the second lemma statement. Okay. Lemma. The second de Giorgi lemma, kinetic. It's exactly what you expect. So F solution this time, not subsolution. To the model problem as before, with same assumption. Then there exists a constant so that you reduce the oscillation. So the reduction of oscillation has to be understood exactly as you would expect. You remember before it was ball 1/2, ball 2. Now it's cylinder 1/2, cylinder 2. So that's my reduction of oscillation. From that, you deduce the Hölder regularity. So look at the picture how it works. You have Q2, you have Q1, Q1/2. And by shrinking the cubes, you will prove the Hölder regularity at the final point. Everything else is similar. So let me skip that. Then the reduction of oscillation, what we discussed is that it is implied by the, you remember, the decrease of the maximum, which is implied by the intermediate value lemma. That chain of argument is exactly the same in the parabolic and hypoelliptic case. What is really hard is to prove the intermediate value lemma. What I'm going to do is I will introduce another tool, which is a sort of, I don't have a good name for it, a kinetic Poincaré inequality. So that's what I'm going to do in the last 25 minutes. I'm going to state that, prove that, and tell you that it implies the intermediate value lemma, and then you have the whole chain of argument. In some sense, it's sort of rehabilitating the original ideas of Nash and Moser. So, theorem. So the very first forms are in the paper with Jessica in 22, but the form I give takes advantage of the 4 subsequent papers. You consider F subsolution non-negative subsolution to the problem at hand in some big open set. You consider 2 for once I give you another center. You could put it back to 0 if you want by translation. Stated like that, I mean the reason I give you that for any pair of cylinders included in the open is that it's very reminiscent to something I spent some time on when I exposed the idea of Moser, and I told you Moser really derives something from this bound on mean oscillation. We're going to give a sort of equivalent of that in the kinetic setting. The bound is slightly weaker. It has to be because there is this transport vector field. Then, and of course the constant is universal, we have that the averaged, that always means I divide by the measure of the domain, the averaged integral on Q R of Z0 of F minus the average of F on Q minus R0. I'll have to tell you what it is. Positive part. I'll do a drawing on the right in a second. Less than, and it depends on all the usual suspects. The dimension, the capital lambda constant, everything is less than the average integral of the gradient of V of F and on Q capital R0. Okay, so now I'll make a drawing and let's try to discuss and understand that inequality. So you see it is a way to measure oscillation in a very weak form. You're saying that, so you have a large domain in which your solution is defined, and then, so I work here, and then here this is my QRZ0, and then I have another cube here, QRZ0 minus. Okay, so I'm saying that F cannot be too much above the average it had here. So let's put it differently. Let's test this inequality differently. If the grad v of f was 0, if f was constant in v, f couldn't move above the average it had in the past. What is powerful in this inequality is that the right-hand side has only the gradient in v. It's not clear at all that you can control f minus an average with just a gradient in part of the variable. If I had put all the variables, it would be a sort of Poincaré inequality standard. Okay, so it is a sort of measure of oscillation, and I have to give you a precise definition. So soon we'll center everything at z equals. You can center things at z not to be 0 to make life simpler if you want. But here is my definition of.
Sorry, Clément, can you say, how do you define the Q minus?
I'm writing it now. So, so you remember that. Let me write the two cubes I'm dealing with. Right. So I have a large cube, which is the one with big R. Which, okay, you can plug big R in that definition to remember what it is. Okay, it contains everyone. That's where I have a solution, and that's where that's what I will use to collect all the gradient error. And so this one is the region where t minus t naught is between 0 and minus r square, and x minus x naught minus t minus t naught v naught less than r square, and v minus v naught less than r. Okay, and now this one, these two things are the same, but I modify that. I translate it as the picture suggests. I push it in the past, and that's the only difference. This one will be, the time will be t minus t naught less than minus 2 r square up to minus 3 r square. So visually, this is r square, this is another r square, this is another r square. Okay, I leave a gap of the same size typically. The gap here is needed, by the way. In that argument, the equivalent of the parabolic equivalent of that argument, intriguingly, doesn't need that gap. I don't fully understand intuitively why, but we have counterexample in the kinetic case. Okay, so now before I prove this Poincaré inequality, I would like to motivate it to show you that it's useful. I will give a very simple argument to show why the kinetic Poincaré inequality implies the intermediate value lemma, and therefore you have the whole proof. But like I said, you have the chain of argument. Okay, so kinetic Poincaré implies kinetic intermediate value lemma. So I have to formulate it. Lemma, kinetic version of the Giorgi intermediate value lemma. So it goes like that. Fortunately, I have my picture. So I take F. It's the same setting. Obviously, because I will use Poincaré to do that. Same setting, so F sub-solution to the problem in my large ball. And you assume, from now on, let me drop the base point. You can translate and go back to 0. And I assume the following estimate. So in the past, I have mass below 0. Because I skipped the parabolic case, of course, it looks like very new. In the elliptic case, there was no past and future. You would have seen that already in the parabolic case, but I had to skip it. So you see, before my conditions in measure were in large ball, smaller ball, there was no time. now I have a condition in the past that I was quite often below 0. So I will ask that this is greater than, let's say, A1, or whatever we call it, delta 1, sorry, measure of Q R0 naught. So it's a strictly positive proportion of the cube. And in the future cube, I spend time above theta. The statement is that there exists theta so that if you have these things for two constants, then the region where f is between 0 strict and 1 minus theta strict in a cube in the future, but even smaller. So let me represent it on my picture. The conclusion is in this cube, even smaller here. Then this is greater than some constant new measure of the cube. And in fact, from the proof, you even get that this nu is of order delta 1, delta 2, provided you adjust theta and the deltas properly. So it's potentially very small, but you have an argument. So how do we prove that? So you see the argument. I have some here. F below 0 happens enough. In that future cube, f above 1 minus theta happens enough, then there will be intermediate values there. So you just have to account for the time variable in order to state things properly. Proof. So it goes like that. So we have, remember that we will use, obviously, so f plus is also a subsolution. So if f is a subsolution, f plus is as well. So I'm looking at that. Yes. And I want to use that in order to get bounds on the intermediate measure. So I'm just giving you the sketch of the argument, which is that this part is reminiscent of the third argument I gave in the elliptic theory. So the idea is to look at the average. So the average in the past cube. Can we understand that a bit more using the assumptions? It's an average of f plus in the past cube. But because of, oh, sorry. I forgot to put a huge assumption. Ah, my mistake. So f is a subsolution less than 1. Sorry. Of course. As in the intermediate value lemma in the elliptic case. Okay, so now that, because f is less than 1, this integral is less than the integration where, so 1 over the measure times integral where f plus is not 0. Right? just because, just because this is less than 1, I can always reduce to this. So it is less than the measure where f plus is non-zero. And that is actually exactly less than 1 minus delta 1. Why? Because the complementary of that set occupies a proportion at least delta 1 of that set. So that's exactly my first assumption. Okay, so now I go back to the left-hand side of my Poincaré inequality. And now what can I say about that? Well, if you look at the positive part of f minus a cutoff line, it's always less than the same thing if you lower the line. Right? So I can take an upper bound on that, and I only increase the integral because it comes with a minus. So this is less than integral of f plus minus 1 minus delta 1. Now, if I restrict to if I restrict, it's bounded below, sorry. Bounded below like that, And now if I restrict that domain to, it's a bound from below, I restrict to where f plus is greater than 1 minus delta. And now what do I have? This is greater than 1 minus delta minus that, so I have exactly delta 1 minus theta. You can drop the plus, you just take theta to be delta 1 over 2, for instance. And you get that it is bigger than. So you have the measure of that set. Greater than, you can drop the plus 1 minus theta divided by the measure of the set times delta 1 over 2. But now, by assumption, this is greater, this whole thing is greater than delta 2. That's my second measure assumption. Okay, this is 1 minus theta, sorry. So this is greater than theta 1, theta 2 over 2. Okay, so we are in good shape. Look at the Poincaré inequality. My left-hand side controls from below the product of the two measures. So now I have to work on the right-hand side. You can really recognize here, the sort of argument I did in the elliptic case. So in the right-hand side, you just say that it's an integral of the gradient v of f plus, and it is on your cube, and it is the integral on the cube inter where f plus is 0 plus the integral on the cube inter where f is between 1 minus theta and 0 strict, and it's the integral on the cube inter where f is greater than 1 minus theta. 3 parts. The first part is 0, because this is the gradient of a positive function, so where it is 0 doesn't appear. The second part is what I want, because it will estimate the measure of that set. The third part will be small. Why? Because of the energy estimate. So So second term, first term is 0. Second term by Cauchy-Schwarz, this one gives you a measure of the set I'm interested in to the power 1/2, and then I have an L2 norm of the gradient of f, which is controlled by energy estimate. Okay, we can always control by energy estimate the gradient in V. It's a gradient only in V. And the third part, which is the funniest part, you have grad f plus on f on the cube and f bigger than 1 minus theta. Because it's a gradient, I can remove a constant, right? Doesn't change anything. So in fact, because I can remove a constant, I can just just bound it like that. And that object now is, that's a new subsolution. So this object is between 0 and theta. Because f was between 0 and 1, and I only look at it in this region. Okay, so, sorry, that object with a plus. Sorry, I forgot. Without the plus, it would go below 0. So that I have a subsolution between 0 and theta, and if you estimate, let's call it g, if you estimate the gradient of g in the energy estimate, it will be less than some constant, the L2 norm of g. That's the energy estimate that tells you that. You look at the L2 norm on a finite set of something smaller than theta, that is less than theta square. So that's the energy estimate is a scale invariant version of relation between L2 and the gradient. So it says that if you're small, then the gradient has to be small. So this is a small error, and by taking theta small enough, you can indeed make sure that term controls from below the product of the measures. So I'll take 5 minutes to explain the key steps that remain is the Poincaré inequality stuff. So maybe let me write it there.
So all the hypoelliptic structure is hidden in the Poincaré, no?
Yes. Yes, all the work, that's yeah, absolutely. Which, I mean, it's a question of taste, I imagine, but for me, it's a big advantage. Because now we've reduced the problem to a functional inequality that captures everything. Absolutely. But you could have said the same. I mean, even if I didn't call it like that orally, but I put it in a note. In the first de Giorgi lemma, the kinetic version, the key step for which I gave 2 approaches, averaging lemma or fundamental solution, you could call it a kinetic Sobolev embedding. In the end, that's what we did. We control a gain of LP integrability, in fact, in terms of only L2 and H1 in V, and being solution to the equation. Yeah. I don't know if I should call them functional inequalities because they are valid for solutions to an equation, which is a very bizarre type of function space. Okay, so I'll give the idea of, once we have done all that cleaning of the kinetic Poincaré inequality, the reason it is formulated like that, it's to allow, so you have a subsolution, and this one is as a variable in the future, this one as a variable in the past. Let's rewrite it in a slightly more schematic way. Q plus, I'm changing the notation slightly. Q plus is the cube in the future in my drawing, which of course I've erased. Okay, I have a Q plus here and a Q minus here, living in a whole cube where I'm solution. So here it's taken in the future, here it's taken in the past, and I put a plus here. So another way to think of it is, because all my integrals are averaged, that is taken at the plus variables, and that is taken at the minus variables. Yes, okay. So this one has the ds minus, and this one has the dz plus. Okay, so the reason we do it this way, and it's important to go from past to future in this way, there is a positive part here. We're going to take a trajectory. And now the trajectory will not be a straight line. We're going to take a trajectory that connects any past point to a future point. Okay, so we'll have a trajectory gamma that goes from the past point to the future point. I will connect every past point to a future point like that. And then I will write a Taylor. That is the part that really has some inspiration from the argument of Alexis in the elliptic case. I will write down something like a path integral, right? So I'll have d over ds, let's call it s, it's not time, it's a parameter of my path, f composed with my path. Makes sense, right? I have a path like that.
Arbitrary choice.
No, absolutely not. The goal is I want that thing to be less than only the things I control by the equation. So what I can afford is anything of that style because I have the energy estimate. That is fine. So in terms of vector fields, I'm allowed to move anywhere I want along the elliptic part of the variables. And then I have to, the other term I can make appear with exactly that sign is the transport part like that. Not with a minus, with a plus. And it has to be. It's because I have to go from past to future. It's the time arrow in the problem. And for that one, I will use the PDE to say that it's less than that. So I'll make appear this other vector field, then use the PD to replace it by this one, and then do integration by part and work on that one. So the geometric setting is that I need a path gamma that is created by the Harnack vector fields by T and grad V. Of course, there is way more general versions of what I'm saying for general hypoelliptic problems. We've written that. But in general, you want a trajectory that is only created by that. The first one we did with Jessica, because I don't have more time to give you an avalanche of formulas, we'll finish with drawings. So this is really an hypoelliptic trajectory. We want a trajectory to connect any point based on the Harnack vector fields. The problem is, there is a problem. The ID looked correct, so we spent a good few months on that with Jessica because it looks very much correct geometrically, and when you start writing it, there's a big problem, which is that you have to be able to make your integration by part here only with respect. So it looks like technical, but it is not. We shook it all the way possible. You have to fight this difficulty. You have to do it only with respect to the past variable. Because this is the only variable you have to do an integration by part. The plus positive part is a very non-smooth object. You can't swap it with anything. So you want to perform an integration by part with respect to a past variable, but look at what it means. Let me redo the drawing. You have a trajectory like that, and you're somewhere along the trajectory. When you're close to the departure point, it's still very okay to parameterize yourself by the departure, and it's non-singular. And you'll be able to do your integration by part. When you arrive close to here, you obviously I mean, it's visual, right? This point is fixed. The way you parameterize the curve obviously becomes singular with respect to the initial starting point. And the problem we had with Jessica was to tame this singularity, to make it integrable. So the first trajectories we did with Jessica was the following. You start from a point S x v in the past. That's my point in the past here, z minus. We wanted to connect it to z plus, which was t y w. And we did the simplest way you could commute the amount of vector fields. We said, well, first, change the velocity, adjust it to the one you need. We know we have a gap in time. So we adjusted the velocity to v minus w over t minus s. Then we ran the free transport that changes s x to t y. And finally, we ran again the change of velocity to bring the velocity back to w. That's a way to commute the vector fields. The problem is that doing that, the singularity was non-integrable. So at the time with Jessica, we added a very annoying technical part of the proof. We added a tiny bit of the forbidden vector field, which we dealt with by this form of averaging lemma I was talking about, tiny bit of Sobolev regularity. So then we got rid of that thanks to discussions with Lucas Niebel and Rico-Zacher. So the idea is to consider another type of trajectory that is actually like an inverse power, slightly singular, but in a way that makes the change of variable better. So it will sort of want to escape very fast from the initial point. So you see what I mean? And then you will make the singularity, instead of being -1, will be -1/2. So let me give you the final formulas, and I stop on that. So in the end, we solve the best way to visualize a trajectory that is created solely by the Hermander vector field is in fact just to solve the Newton equations. That's very simple. So you want, in the end, you want to solve your trajectory obtained by solving v dot is equal to a certain force, x dot is equal to v, and that's it. Okay, so you just want to solve that, and I assume that my time will move linearly with my parameter. Okay, so the time will just do. If you don't do that, it's just a change of variable. It doesn't matter. You have to fix one of the three variables. You have too many freedom. So for the time, I will just go from my S. Oh, okay, I called it S, and my parameter was S as well. Sorry. So let's call that R. Okay, if you let me. So the time will just be S plus R t minus S. R is the parameter of my trajectory. And now you want to solve the Newton equation to connect any pair of points. After a lot of, in the first calculation was awful, and in the end you can make the calculation super simple. We realized you can just take A1, you can just take, when you have two commutators, 2 is enough. You just take two vectors like that with R minus alpha 1 plus A2 R minus alpha 2, where alpha 1 and alpha 2 are two powers that must be different in 0, 1. But they are not one. They are not two singular. The force is not two singular. That's the key point. We need 2 in order to have enough independence to connect any any pair of points between past and future. And recently we wondered whether we could get the critical scaling, the critical trajectory, which is scales like -1/2, because it gives the critical scaling in the Harnack inequality and a lot of other inequalities. And in fact, you could do something better with a force. So it's really a control problem if you think of it. We just adjust the force in order to connect points. we just did r minus 1/2. If you just do this, obviously you kill the independence and you don't manage to reach any 2 points. But we could squeeze some logarithmic oscillations. Don't forget r is strict positive. So by squeezing logarithmic oscillations, we can reach the 1/2 scaling. And we have an argument for which it's optimal. And you can, there's a way to do it with any number of commutators you want as well. It's just, and it's you have the optimal scaling that depends on the number of commutators and everything. So the moral, I'll stop here. The moral is that in the end of the day, this mixture of, it's a mixture of Nash, Moser, Kruskov, and Giorgi, which reduce the whole chain of argument to this kinetic Poincaré, which measures oscillation between past and future. And we can, that we can look at with trajectories, which I hope is more robust for problems.
Thank you very much. Any questions?
So if you, at the end of the day, when you proceed in this way, can you, do you get an effective Hölder estimate in the end? You get effective Hölder exponent, which you would not get by the method in our paper, or?
Well, we get quantitative Hölder exponent, but we could get before. Yes, the scaling. What is improved by? Okay, the improvement here is the dependence in the capital lambda. We have the dependences in the Harnack inequality in capital lambda. The type of dependence is optimal that we obtain.
Ah, okay.
And the dependence...
The modulus of continuity is going to be optimal.
And the way it depends on capital lambda, the form of it will be optimal as well.
On the ellipticity bound?
Yes.
Ah, okay.
No more than that. In particular, you could... I'm not claiming we know how to get whatever it would be the optimal alpha. That's not what I'm claiming. And as well for Harnack, you could give another meaning to the optimal constant, which would be the one for which that would be saturated by the fundamental solution. But that would be a crazy strong Harnack inequality. That's not what we can prove. But we can prove that we obtain the dependency as it should be in capital lambda.
And so suppose that you, I can't remember, there's this paper by Zhu, right, where he does the same type of result, but with an advection operator that involves a B of V, for which the lossy averaging method is absolutely necessary, I think in this case, especially B is low regularity. So in that case, do you also get a... Can one also apply this approach and get an...
So I don't know yet, because we thought we would look at it, and I had no time yet. In particular for relativistic operator, it's very interesting what you say. So Loher-Rebucci, for instance, was interested. I would be hopeful, because it's a method a bit like averaging lemma that is not relying on fundamental solution. It's quite robust in the end. Yes. You really solve your control problem. There's a lot of intuition. You know what you're doing. In the end, you're finding a force to connect point that is not too singular. And the rest is pretty systematic. In terms of extension, what is done is the adaptation of all the quantitative trajectory approaches to non-local operators. That's what Amélie did that in her PhD. But I had no time here.
Maybe one quick question. So compare with the other method you explained yesterday with the collision of scale and so on, which were somehow very dependent on the operator structure. This would not go through with.
Yeah. Oh, that's a good point. I had no time. I can show you one thing that connects everything. Yes. So the Poincaré inequality is really similar. It's at the de Giorgi level, let's call it like that. In the de Giorgi approach, the collision of scale is hidden because it never takes the log. You don't see it as when you take the log. Okay?
Yes.
So our method of trajectory is not taking the log. But if you track down everything we do, so connection with the log. So it's partly an answer to your question. If you track down everything we do, in the end, the decrease of the maximum is can be formulated, I mentioned it once, as a measure to pointwise estimate. You remember. So you measure in the past how much f was less than 0, and you obtain in the future that f is less than 1 minus lambda. You remember, it follows from the intermediate value lemma by a finite induction. Yes. If you now quantify everything, this lambda, everything, how it depends on everything, you change the constant here. You really, you shake everything in order to understand how all parameters depend on each other. In fact, this proves, in fact, it's equivalent because it's true at every scale. It is equivalent to a weak log Harnack inequality. So that is the best connection I could give you. That, if you formulate it on each and every level sets, you will obtain that it proves that the log of f to some, or maybe, okay, like that, to some powers, a small power, in fact close to 0, is less than the inf of f with appropriate cubes. That's called the weak Harnack inequality. Okay. Right? So you see a connection with the log here. Mm-hmm. In the de Giorgi approach, the collision of scale appears only with the use of Sobolev embedding. Okay. In the Nash, Moser, Kruskov approach, you see this beautiful universal estimate for free on the log. But my claim is that the universal estimate for free on the log is obtained by de Giorgi here. Okay. He's proving an estimate on the log that this sort of Harnack universal inequality also comes up from nothing.
But that, of course, but at least at the level of the operator, there's no direct proof. I mean,
in de Giorgi, you never take the log of the solution in de Giorgi. Okay. Never. I mean, it has advantages and drawbacks. The advantage of not taking the log is that at least we can do trajectories. We know what we're doing, mechanically speaking. And last point is that actually to go from that to the true Harnack inequality, which would be a power of f, you have an argument from elliptic theory that we adapted to the hypoelliptic setting, which is entirely based on the scale invariance of the problem. It's nothing to do with the PDE. If you have proved that everywhere with scale and translation invariance, it self-improves into the real weak Harnack with the power. That's also a manifestation of universal bound from nothing. That's the best dictionary I could think of, but the two approaches are not exactly framed the same.
Well, thank you. Are there more questions? So if not, thanks again for